So welcome everyone to our climate physics seminar series. And so today I'm very excited to have, we're excited to have Justin Burton to give a talk. And Justin has worked on really a broad range of problems, and you can find Justin's work in both the physics community, in particular in salt condensed matter, as well as in the climate physics community. And Professor Justin Burton obtained his bachelor's degree in physics from the University of Cincinnati, and his PhD degree in physics from the University of California, Irvine. After he did postdoc at the Fred Hutchinson Cancer Research Center at the University of Chicago, he joined the physics department at Emory University in 2013. And he's now an associate professor in physics there. So Justin's research is really deeply interdisciplinary. So his work is mostly experimental and cover a range of topics in complex and non-equilibrium systems. So the work that he's working on right now include interfacial and nanoscale fluid dynamics, disorder, granular materials, machine learning of many-body dynamics in dusty plasmas, and the physics of tight water glaciers. So I think we will probably hear about a few of these projects today. And he received several awards, including the NSF Career Award, the Arthur Compton Lecturer at the University of Chicago. And he's also a member of the editorial board for Physics Review Research. And so one of the things that's worth mentioning is that he's also heavily involved in outreach events. So his group leads a number of K-12 STEM outreach and educational activities in the Atlanta area. And with that, so it's exciting to have you here, Justin. Feel free to take it away.
Thanks very much for that very nice introduction, Yao. So look, these GPC seminars have been going on for a while, and I think they've been really successful. You know, part of the reason that we created them, and Yao and Pedram and Albion and other people have really been making them happen. But one of the reasons that we wanted to create them is to kind of educate the broader physics community on kind of interesting problems related to climate, and that's what I want to do today is focus a little bit less on my own research, although you'll hear about some of that stuff, but also just kind of give an overview of some of the interesting stuff that's going on that I think could be of real interest to the physics community. And so I'll have a number of examples that I talk about throughout this talk, mostly examples that are amendable to experiments, because I'm an experimentalist by trade. My PhD was in condensed matter physics, studying quantum fluids at very low temperatures, and I've kind of meandered around different research topics and seen quite a few different ways that people approach things. So hopefully, one of the goals here is that we were able to inspire young scientists to work on climate problems. Let me just there we go. Okay, so I wanted to show this picture first. Just, it kind of throws people off always, when you see the world upside down, so to speak. But just to remind everybody that, the Earth has rotational symmetry, and things we see on a map are not the way things really are on a sphere. And so there's lots of things going on in this picture, right? There's fluid dynamics, there's geomorphology, there's oceanography, there's all kinds of things. And when we think about climate physics, that applies to a kind of a broad class of problems. And I'll tell you about some of those today that have really piqued my interest over the last 10 years. This is a real picture, by the way. So, this moon down here, although it almost looks kind of fake, I don't think it is. This is from NASA. Okay. So I wanted to say just a few things about the topical group on climate physics. Most of you are listening to this talk, I'm sure, are members. If you're not, you can definitely sign up to be a member. And GPC was created a number of years ago and really kind of aims to do what the highlighted phrases say, diffuse knowledge concerning the physics, measurement, and modeling of climate processes. And I take a broad view of that statement there. But also integration of scientific knowledge and analysis methods across disciplines. So it's inherently interdisciplinary, crossing boundaries. You'll see the GPC show up at the Division of Fluid Dynamics meeting, the APS DFD meeting. We have kind of a home base at the APS March meeting, and a number of us also attend the American Geophysical Union meeting. So we naturally are kind of spread out through many different research fields and professional societies. But climate physics is broad, but it's not well represented in physics, unfortunately. So this is just some statistics, the most recent ones that I could find from AIP, showing kind of a distribution of how PhDs are obtained in most physics departments. Condensed matter physics is by far the largest, followed by particle physics and fields, astronomy. And you notice you go down this line and you don't see climate physics really anywhere on here. Maybe you can shove it into complex systems research or something like that. But it's still rather small. Yet we all, one of the reasons we're here is that we all know that it's really important, right? So why aren't more physicists choosing to work on these problems, and what can we do to inspire more young early career scientists to think about these problems? That's one of the goals here as well. So a big boost came, in 2021 when Manabe and Hasselman, along with Parisi, shared the Nobel Prize, partly for their work on climate physics. And this was a fantastic moment. But from an experimentalist point of view, climate physics, I think in the young student's mind often presents an image in the mind of large numerical models and theory work based on atmospheric and oceanic flows, and that is definitely true. That is, kind of some of the most important part of climate physics, figuring out how CO2 affects, the temperature and other parts of our atmospheric system, and also how the oceans are going to deal with increases in CO2, and how these flows work on a spherical surface, and thinking about the Earth as a heat engine, right? This is an extremely complex problem that is, amendable to large numerical models. However, as I want to point out, more than half of recent physics PhDs are in experiments. Students are attracted to fundamental questions and problems, when they're thinking about a single electron or something like that, or maybe, pairs of electrons, and thinking about superconductivity. It's a little bit maybe easier, or maybe they're just used to thinking about things in this way. The Earth and its climate are messy, and more is different is a statement that's kind of hard to convey to some of these students, that there are really fundamental, interesting problems. Manabe partially won this award for his work on climate models, and one thing I really liked about Hasselman's work was thinking about the climate as a stochastic system, and how different timescales are integrated in this stochastic system, and so there's really some fundamental work there that should definitely be highlighted. I'm going to take a slightly different approach for the rest of the talk and kind of focus on something else. That's not to say that they're not interesting experiments that can be done dealing with climate problems. This is one that I was that I read a few years ago that I really liked, where they were doing kind of experiments in the lab, looking at this quasi-biennial oscillation that has this weird period of 28 months that's not in the Earth's atmosphere, that's not really kind of an integer fraction of a year, and by thinking about basic nonlinear problems in fluid mechanics and bifurcations and connecting these to nonlinear dynamical systems, you can learn a lot about what goes on in the atmospheres and just the basic time scale. So experiments can be very useful, even when thinking about atmospheric related problems. You don't necessarily have to just be very good at large numerical models or something like that. when thinking about the climate, or at least this slide, I really like because, I wish I had a slightly higher resolution, but this is the one I could find. But it really kind of underscores the way I think about climate problems, right? There's so many different parts to the Earth's climate. I have been doing a lot of work in cryosphere and branching out a little bit since then. But I mean, there are just so many interesting problems in all these areas. Not only are they related to earth science, but also a lot of them are, changing. The state of the field is changing rapidly because of climate change. And so there's a lot of things to work on. And the span or the space is very broad, and lots of rooms for a lot of room for new students. So today you're going to hear about a few examples, but I'm going to talk a lot about the cryosphere and processes that happen in the cold areas of our planet. So when thinking about climate change, the atmosphere and maybe the oceans are the first thing that we go to, but the consequences of the climate change sorry about that, can hit home, right? I mean, from wildfires that produce smoke and tiny particulates to flooding, to dried, parched lands and crack patterns, and kind of coastal areas. Climate change is something that's happening right now on the ground beneath our feet. It's not just temperatures and carbon dioxide going up. It's something, the physical consequences that are beginning to be something we have to deal with every day. And there's a lot of physics problems associated with these. So the goal of this talk, as I think I've already kind of mentioned a little bit, is, climate physics touches many aspects of our lives. It is broad, messy, but also necessary. And there are more interesting problems to work on than researchers to work on them. That's one thing that when I was a younger, early career scientist, that's one thing that I was really concerned about. I wanted to, in order to make an impact, you want to have a lot of space in front of you. You want to have lots of different choices of problems to work on. And I think climate physics is kind of one area where that's definitely true. And so there's plenty of opportunity for theory, numerics, observation, and experiments. And you're going to hear a lot about experiments today. So hopefully there will be some inspiration for early career scientists, and I'll give some examples of problems that I have found interesting over the years, and including ones that I've worked on myself. Okay. And so this thinking about the Earth as a soft matter landscape, which was in my title, is something I borrowed from this really nice review paper that was written in 2019 by Doug Jeromack and Karen Daniels, and where they review kind of a lot of the ways we can think about Earth's landscape evolution as soft matter. And this a lot of times involves thinking about grains that are embedded in some kind of fluid, which is actually a really broad statement. I mean, we could think about atmospheric dust blowing off of the Saharan desert, which eventually lands in South America. Close my email window. We could think about, hill slopes failing and, debris covering roads. And, this often happens when you have, very dry land that, is then saturated by heavy rain and things like that. And trying to predict when this is going to happen, kind of a big issue for safety, but also for, just, trying to figure out when granular materials are going to fail is a broad problem that goes beyond, just climate physics. We can also think about, ice as a granular material in many respects, and that's something you're going to hear more about later. So I just wanted, if you haven't seen this paper, I encourage you to read it. It kind of gives a great overview of some of the ideas that I'm going to present in this talk today. So give you an example of the way kind of experimental physics can address some of these problems. I'm going to give you two examples of experiments that concentrate on just kind of granular flows. I mean, even a sand pile has really interesting physics, and which needs high resolution experimental techniques to understand what's going on sometimes. So one example, one of my favorite examples is this one from just a few years ago. which uses kind of speckle patterns of light to look at extremely small strain rates in just the relaxation of a pile of sand. So, you pour a pile of sand and it looks like it's not moving, but actually it is over very long time scales. And it's dominated by kind of small rearrangements and avalanches, as you can see with these heterogeneous patterns here. But from a physics point of view, the reason I like this so interesting is because it uses, interference of light, which is one of the most sensitive techniques we have for detecting things. Even detecting gravitational waves. That's not using interference of that's also using interference of light to detect, kind of small deviations in space-time in that case. But, using kind of these really ultra-sensitive techniques can teach us a lot, even about something as simple as seemingly simple as a sand pile and how it relaxes. Sticking with sand piles just for a second, we can think about how sand piles interact and move around. In this experiment here, they're modeling sand dunes and how they interact. And so they have kind of a large experiment where sand dunes are created and, they're constantly in this kind of rotating flow, and they repel each other, and they move around and they interact. And so, this isn't something that you would find in, maybe your standard physics curriculum, how sand dunes interact, but there's really a lot of interesting features and more than just this one paper here, but this is Natalie Brenn's group out in Colorado. Okay, so these were kind of two examples that I wanted to show you of how kind of experiments can address problems in at least granular physics and earth science with relationships to climate physics. But now I want to turn attention a little bit towards kind of the cryosphere, which is where I've spent a lot of time thinking about problems in the last 15 years, I would say. I like this cartoon because, it's cute and it has lots of different areas that I'm going to talk about. So, for example, you can think about problems in mountain glaciers. You could think about problems at the bed of ice sheets, which I'll talk a little bit about as well. And you can also think about problems kind of on ice shelves where the ocean meets the ice. This is where a lot of dynamic processes are happening. From a climate physics perspective, the cryosphere is extremely important. Many of you maybe have heard the statistics, how much fresh water does Greenland hold, for example? Well, it's about the equivalent of 20 or so feet of sea level rise, right? Or 7 meters, something like that. Antarctica is way more like 200 meters or 200 feet of sea level rise, but we're not really worried about Antarctica melting in the short term, but parts of Antarctica. So the point is, even small changes in the amount of ice in the polar regions of our planet can have huge impacts to sea level rise and the reflectivity of certain parts of the Earth when it comes to solar absorption. So it's a really important part of Earth's climate system, but also has really interesting physics going on the small scale. Okay, so I'll tell you about a few problems that I found interesting. We'll kind of start with up here high in the mountains. There are these really cool features kind of in the Andes Mountains called penitentes that were first noticed by Charles Darwin more than 100 years ago. And they're like these really sharp, pointy, features in the ice. And then you can ask, from a pattern formation point of view, you could think about how would something like this form? They're only found really in these kind of high altitude mountain glaciers. And the answer is kind of interesting. It's sublimation, right? So, and it's the way that the sun impacts the snow itself. So, up in when the sun's shining straight down, it's able to kind of make these penitentes form. Just basic ray tracing can kind of illustrate some of what's going on here. Whereas if the sun is at too much of an angle, then it ends up kind of making these sinusoidal perturbations on the snow shrink instead of grow. So it's kind of a linear stability problem. It's a feedback analysis, and it all has to do with what is the inclination of the sun with respect to where the ice is. So this is one problem that I was kind of saw evolve and always thought that was really interesting, a pattern formation problem that involved the sun, actually. So this is some problems in mountain glaciers. I'll kind of move to Greenland here, and thinking about some problems in more on top of ice sheets. One thing that's been accelerated due to climate change are the formation of these moulins, or these kind of giant holes that form in the ice sheet that drain an enormous amount of water. It's really quite incredible how much water can drain through these holes. I'll show you a video here in a second that I just found on YouTube. And so, you have all this meltwater that literally drains into these chasms, and you don't want to fall down in one of these things. They don't stop. They go, 3 or 4 kilometers down all the way to the base of the ice. So it's really quite daunting when you think about it. Nothing's coming back if you drop it down there. So what's going on here? This is kind of a cartoon of the types of things that are happening on the Greenland ice sheet that people are thinking about and working on. So you get these glacial lakes that form, and these lakes eventually, now you got to remember that water is denser than ice. So water will eventually push and fracture and melt its way down all the way to the base, and you get these long moulins that form that transport water from the surface all the way to the bottom. And this is kind of important. When these lakes drain, they can affect the sliding behavior of the ice sheet against the bedrock, because it adds all this water and it lubricates it. So there's a lot of consequences to adding extra water at the base of these ice sheets. And there's a lot of interesting kind of physics problems as well. So, for example, you get these dissolution networks that control meltwater drainage. And so if you think about water trying to push its way underneath one of these ice sheets, well, you might think that it just spreads out smoothly in kind of a thin layer, but that's not what happens at all. It channelizes. And so you have this balance of water, which is melting ice as it moves along and applying a pressure that keeps the channel open. But also, if the water slows down or something else happens, then it can collapse. It can erode the soil away below it. You get coalescence of channels. You get dendritic patterns. If you model the physics of these kinds of these channels, you get, like I said, coalescence between these channels, and they evolve over many days. So when just thinking about dendritic patterns, which form in all different types of areas of physics. This is one place where, it has a direct, you can feel the water drainage with a seismometer. That's one way they can detect kind of accelerated motion of glacial beds is through seismicity. So, this is also another kind of interesting problem. One that's a little bit challenging to do experimentally, but, this was a numerical study. One of my favorite kind of experiments, in physics, we love big experiments, right? CERN and other places have kind of large experimental facilities, but you can have this in climate physics too. So in Lucas Zoot's group at UW-Madison, they have a large experiment where they're exploring the interface between this kind of frozen granular material that exists beneath glaciers and the ice on top of it. And, thinking about the slip and flow law right at this interface is really important, because it's something we can't see. It's kilometers below these ice sheets, but it's really important for modeling the evolution of these ice sheets, and something, a small change in your boundary conditions can have a big change, decades down the line. And so they have this large experiment where they're investigating this slip law by, watching the granular material deform underneath this ice, and keeping it all cold with antifreeze. And so, if you're a young physics student and you're interested in, kind of large experimental apparatus, there are plenty of avenues for this as well. So I'm a big fan of these experiments, and I just wanted to highlight them. Okay, so we were talking about Greenland just now. I'm going to kind of move down to Antarctica and show you kind of a picture of what one of these giant icebergs breaking off Antarctica looks like. This is kind of what is very typical. You might get these 50-kilometer long icebergs that break off and they just float away, and they might last for years. Some of these icebergs, you can put GPS sensors on them, you can track them, watch them move around the Southern Ocean, and it takes a long time for them to melt. But keep in mind that they're only about maybe 500 meters thick, so they're really like a big, long, flat plate. Not that 500 meters isn't a large size, but the iceberg itself is 50 kilometers, or something. So they just float away, and it's kind of a quiescent process. But that's one way that Antarctica loses a lot of mass, but it's not the only way. It can be a lot more explosive than that. And so this is, I'm going to show you a series of images from the Larsen B ice shelf. This is actually the problem that got me interested in, kind of ice in the first place. And I'll tell you a little bit about it. So this is Larsen B ice shelf from 2002. It's, almost 20 years ago now, but this is not the only time that this has happened. It's one that we happen to have a high resolution images of. And so what you're seeing here, all this ice is over top the ocean, but what you're seeing all these little dark splotches here, and what these are lakes. These are, kind of lakes that formed on there, and these seem to show up and become more prominent right before something massive happened. So what happened was you get these glacial lakes that form, and then they drained, and then the whole ice shelf over a matter of weeks kind of busted apart and then completely disintegrated into the ocean. And it was very fast. I mean, if you think about it, this is a lot of mass to move this quickly. And so there's a few interesting physics problems when thinking about explosive ice shelf collapse. If you zoom in on it, you can see a lot of these icebergs are very rectangular and tabular. And you can see also, this is actually a false colored image using different kind of spectral imaging from satellites. So, this is not may not what it would look like with your eye, but you can see a lot of these icebergs are overturned, right? So here's, this side is clearly different than this side. So one was the bottom and one was the top. So a lot of these icebergs that flipped over or capsized during this explosive disintegration process. And this energy released when one of these iceberg tips over actually, we think, had a lot to do with driving the outward expansion of this ice. So it's almost like a chain reaction. And so the way we think about this collapse is that these hydrofracture from meltwater weakens the ice shelf and kind of breaks it into all these kind of narrow pieces. And then these narrow pieces, they're not gravitationally stable. They want to tip over like dominoes. And when they do that, they got to push each other aside. They got to make room and push all the other icebergs out of the way. And that's why this thing expands so quickly. More recent work has focused on kind of how these cracks formed in the first place, and what their relation is to these glacial lakes. One idea is that these glacial lakes, elastically depress the ice, causing ring fractures and other fractures in the ice, which can propagate down all the way to the bottom once they fill with water. Because remember, water is more dense than ice, and that water will want to drive fracture all the way to the base of the ice shelf. And so a number of people have worked on this over the years, and it's a really interesting problem. And I encourage, we have more ice shelves that we think are going to, possibly explode in the coming decades. So, I guess stay tuned, unfortunately. Sticking with ice, one thing, and bringing it back to the idea of soft matter, in soft matter, one thing that we think about a lot is rheology, and thinking about what is the relationship between stress and strain in a material. If I have a linear elastic material, the stress should be proportional to the strain. But, even ice, which is not, one might naively think that it's not complex. You take the ice cube out of your freezer, it can crack. But what you may not know is that in the time scales for glacier flow, it is a highly kind of nonlinear material. So the stress is not directly proportional to the strain. In fact, there's a power law. It's a power law fluid, and So there's something called Glenn's flow law that was been used since the 1950s, when some of the original experiments were done, that over a range of temperatures and strain rates and things like that, assume that the strain rate is proportional to the driving stress to the third power. Now, this is an approximation in a certain regime. The power may be, 1.8, it could be 4, depending on what is the microphysical process driving the change in the flow of the ice. But over a reasonable range, people often assume that it's described by this, kind of power of 3. So it's treated as a power law fluid. These words may be familiar to anybody from the rheology community or who thinks about non-Newtonian fluids. The problem is that's okay when I'm thinking about glaciers flowing over hundreds or even thousands of years, but it also ignores elasticity, fracture, and things like that. So it's not getting the whole picture. Even the rheology of ice melange itself, or not ice melange, I'll talk about that in a minute, but even the rheology of glacial ice itself, it's not a settled story. I mean, here's a paper from 2022 that kind of addresses this individual power and says, well, maybe 3 isn't what we really should be using. Maybe it's closer to 4 or something like that. But actually, there's even more recent papers talking about how, well, compression is very different than extension, and there's kind of they have very different behavior, and they, using modern techniques like machine learning to infer this rheology is really helping us discover something brand new about how ice flows and kind of change the way we think about them. This original data, or some of the original data, actually was all experimental data. So, learning how ice flows, which is like the dominant way that we model how ice sheets evolve on our planet, was, these flow laws were first developed by, kind of precision experimental science. So I just wanted to emphasize that. Okay. But ice is even more complicated. I talked about fracture, and this little GIF here kind of really illustrates the complexity and the fascinating parts of flowing ice, right? So this is Thwaites Glacier, the Doomsday Glacier, if you will, if you read the news, that is undergoing a lot of rapid changes right now. It's being, melted from below by the ocean. But here, what you're seeing is it goes from kind of a flowing, uniformly flowing state, one that might have a relationship where stress is directly related to strain rate at a local level, but then it turns into this fractured granular material. And what we know about granular materials is that, well, the stress really isn't proportional to the strain locally. It's more of a non-local thing. You can, it depends on whether the granular system is jammed or not. There's large correlation links that are important. And so thinking about this transition between kind of steady flowing ice and highly fractured ice is something that, we worry about a lot. I think about it a lot, actually. This is another example of highly fractured ice, but this is in Antarctica this time. This is back up in Greenland, and it's where we have a lot of high resolution data on these tidewater glaciers, these glaciers that focus all the flow of ice from Greenland out into these fjords. And I'm going to show you a movie now from a collaborator, Jason Amundsen, of something called ice melange. So over here, this is all just icebergs floating in the ocean, but there's so much of it, it's just a piled up granular material. And, it's probably hard for you to see. I've been staring at this for years now, so I know where the boundary is, but here is the end of the glacier where this cliff is, and this is all kind of more fractured but still solid glacier ice back here. And just to give you a sense of scale, this cliff here, I don't know if you can see my mouse, but this cliff here is about 100 meters tall. The size scale here is kilometers. Okay, so let's see this movie here. So what you see is this big granular material kind of unjams and starts to move forward, and that releases the pressure on this iceberg, which then now can flip over. And so that iceberg was about 1 kilometer in size, and it even kind of kicked up mud from all the way from the bottom of the ocean, which is 900 meters deep. These kinds of giant iceberg capsize events you can measure with earthquakes. You can measure the earthquakes they create in, as far away as New York City. They usually emit maybe like a magnitude 5 earthquake. But thinking about this giant geophysical granular material as a soft matter system has been really helpful in understanding how it might affect calving of large icebergs, but also, its overall feedbacks on these tidewater glacier systems. So here's a cartoon of what we're thinking about here. So this is one of these tidewater glaciers that terminate into the ocean. There's a lot of interesting things going on here. There's meltwater plumes coming up from below. There's this ice melange, which I'm going to be talking about. It's actually a lot thicker than what you see in this cartoon here, but I like the cartoon nonetheless. You can have large icebergs sitting in the water. There's a lot of ocean circulation going on in here. So there's a couple problems with oceanography and glaciology, fluid mechanics, turbulence, kind of many things happen at once. But we're just going to kind of stick with this granular ice melange and see, is it really, how important is it? What kind of a role is it playing? How does it affect this giant glacier that's pushing it along? So this is just another movie showing kind of a multi-day evolution of one of these fjords that are packed with ice. There's winds, there's tides affecting them. They jam and unjam and stick and slip and move along. And sometimes the ice melange can be hundreds of meters thick, and sometimes it's only a few icebergs thick. And some glaciers are, produce more ice melange than others. I wish I could go. I wish I'd been out in the field to take some of these images. Unfortunately, I've never been there, but so I have to rely on the wonderful images of my collaborators. Hopefully someday I'll get to visit. Okay, so what does this look like? So ice melange is this kind of jammed, buckled, three-dimensional. These particles are not round. They're pointy. They're sharp. They can fracture. I call this iceberg purgatory because it's kind of where the icebergs live before they eventually melt or make it out to the ocean. And it's jammed, which means that it can transmit stress back on the terminus here. And that's kind of important because if you think about the evolution of these glaciers, the boundary condition, the stress at the boundary is a really important part in determining the evolution of these tidewater glaciers. From a granular physics perspective, grains interact through friction, adhesion, cohesion, and inelastic collisions. As I mentioned before, they have a non-local rheology, meaning that the stress is not just proportional to or even dependent on the strain at one point. It depends on, you kind of have to know all the forces and state of the granular system everywhere if you want to know, at one point, which makes it really hard to think about sometimes, but we're making progress on that front. Fluctuations are really important, and I'll say something about that at the end. And correlation links can span the system. So these granular materials are constantly moving through marginality where, the correlation length is, spans from one end to the other. So they're always near a critical point. So we've done some work on this in the past, and these are two papers where there's some experiments in some of these, and the later one here is mostly modeling. But I'm going to tell you one particular story about where we brought in kind of field data and simple models to think about how this ice melange evolves in time. And so, this was a really great opportunity. The paper is listed up here. This was a great opportunity to work with kind of real field data, but also use kind of simple ideas from granular physics to understand, how important ice melange is. And so the field data is the following. They have these two ground-based portable radars that they sit up on the mountain next to the ice. And these things spin around once every 3 minutes and capture both phase information. They're using backscattered radar. So it's interferometry. So you can image the fjord and also but you get phase and velocity information. The velocity would be from the Doppler shift, right? And there's two of them. And you can see kind of the hemispheres that they sweep out here in blue and green. And with this data, we can learn a lot about ice melange and what it does right before and after a calving event. And so the position and velocity of the melange are measured for every 3 minutes for days on end. Okay, so I'm going to show you a movie of what this data looks like. This is the terminus of the glacier. That's where that big calving event was happening. And this is all ice melange here. And the width of this is about 5 kilometers here, just to give you a sense of scale. And these colors, what do these colors represent? Well, these represent essentially the magnitude of the divergence of the velocity field. It's gradients in the velocity field, right? So red would be extension. It's where it's locally being pulled apart. And blue would be in compression, where it's being locally compressed. And so these black lines are calving events. And so I'm going to skip ahead and show you kind of what happens right before a calving event. So initially, you get regions of extension and compression in the melange, but it's very uniform. Okay, so then a calving event is going to happen. And what we noticed, and we were shocked to see, is about an hour before these calving events, the whole thing would kind of decohere. It would look all purple. And it looks purple because you get kind of red and blue pixels right next to each other. And that really means that, you know, we don't have kind of a uniform field of deformation anymore. It's kind of completely decohered. So hopefully we'll get another big calving event here that you can see. It'll decohere again. And then there'll be a large calving event there, and it pushes the whole melange forward. So a large piece of ice broke off and kicked everything forward then. The surprising part about this is that an hour before the calving event, the decoherence starts. You could not see this with your eyes. You could not predict when that calving event's going to happen, yet these interferometry essentially can tell it by the centimeter scale motions of the icebergs. So to give you an idea of kind of what this looks like, Ryan made this nice movie where he plays it forward twice and backwards twice and forwards twice and backwards twice, to give you an idea that these different calving events, sometimes they're really small, but sometimes they're bigger, like that one. That one's a really big one. And so there's a variety of calving events, but in every single case, the melange experiences this decoherence before a calving event happens, which tells you that the melange is the force that it's applying is controlling the timing of these calving events. And so what did we do? What did we measure? Well, if you look at the absolute velocity before a calving in steady state, it looks pretty smooth. It's moving at about 50 meters a day. That's the velocity scale you should be thinking about, 50 meters a day. If you look at the divergence of the velocity, it's also smooth. It has regions of extension and compression. If we zoom in on this little square here, I realize that we have about maybe 5 minutes left, so I'll be finishing up in just a second here. If you zoom in on this little square here, you'll see that the velocity field is very smooth. So here we've plotted the velocity field and we've subtracted the mean velocity. So there's a little bit of vorticity in this particular area that we've chosen, but overall it's still very smooth. In contrast, if you go before a calving event, you'll see that even though the absolute velocity still looks fairly smooth, we get this total decoherence. And if you zoom in on that same area, you'll see that the velocity field actually looks quite irregular, like things are moving in kind of different directions. It's lost its coherence. So we can use these kind of measurements of the standard deviation of the velocity in these little areas to kind of quantify when calving is going to happen. And so this is a busy graph, but I'll just give you a sense of what's going on here. These are 4 different calving events as given by the time here. You notice this data was taken a while ago, but these field campaigns are you get lots of data and you spend years digging through the data, right? So time equals 0 means that's when a calving event happened. That's when a big piece of ice broke off and went into the fjord. And in different parts of the fjord, what you'll see is that this standard deviation, you can plot different things. You can look at the total strain rate or the standard deviation, but either way, these things are showing a marked rise, an hour or more before a calving event even happens. And I told you, you couldn't see this with your eye, but you can see it with these interferometers. And so both in before and after, this melange is showing a way to predict when these calving events are going to happen. It's the failure of geophysical granular materials in real time. And so that's the surprising thing from this graph that you should take away, that these signals that you can measure are increasing and, kind of really go crazy right before a calving event happens. So how should we think about this? We took a simple model of floating granular spheres. I told you that ice melange is not spheres, but we can use spheres to think about it, at least for this particular problem. And we're going to introduce a small strain. We're going to let these floating granular spheres expand just by a little bit. And if you do that and you plot the displacement of any given sphere in that little arrangement, you'll see on average, they experience this overall uniform strain as given by this red line. But maybe a sphere moves 6 meters or 8 meters, and maybe it actually moves less than the average. So there's a distribution. Some move forward a little bit more, some move backwards so there's quite a bit of variation around this mean average. If I just took a piece of linear elastic material and stretched it, that would be the red line. But this is a granular material, and each individual little part moves a little bit differently. You can look at the velocity field in kind of during this extension in our model. And you can look at the histogram of particle displacements and see that it's, fractions of a meter. This is the standard, this is a logarithmic scale, and I've plotted these two dashed lines represent kind of one standard deviation away from the mean. And so it's fractions of a meter. Okay, if we put it all together, what do we learn from this study, right? So the global strain rates can increase by 0.02 to 0.1 per day in the hour before calving. That's this black axis here, the strain rate here per day. However, this corresponds to an overall strain of 0.1 to 0.4%. This is a small change, but in granular materials, that can mean the difference between jamming with large forces and unjamming, so things can start moving. In our model, the particles move about 0.2 meters on average. That's these dashed lines. And this would correspond to about 4.8 meters per day if this motion occurred in the hour before calving. So if the ice melange expands a little bit, it can decohere and release the force on the glacier. And this is an excellent agreement with the measured standard deviation in velocities, which is about 5 meters per day prior to calving. So that's this blue dash line here, where it intersects the y-axis. Okay, so ice melange has been kind of a problem that we've been interested in for a while, and what I hope to convince you is that, at least in this particular study, here's this geophysical, for lack of a better term, soft granular material that has direct implications on the timing of calving events for some of the world's largest tidewater glaciers. So just in the last minute or two, I'll just kind of give you a flavor of what we're doing now. I wanted to talk a little bit more about this. I told you that these problems are amendable experiments, and so now we're looking at floating granular materials, and we're pushing them along, and we're measuring their jamming behavior. This effort has been led by Kavinda and Nandish in my lab. It looks something like this. We have an ice melange that's really just plastic blocks with the density of ice. We have an instrumented movable terminus here that experiences, and the ice experiences friction with the walls, and we push it along and we see what happens. Let me just show you a video of kind of what this looks like from the side and from the top. You get this thick wedge of ice, and you're pushing this granular material through the channel, and we can look at the velocity fields from the top and the bottom. I'll end with just showing you kind of one important thing that's kind of been on my mind recently. Of this here. So if you look at the force that these floating granular materials, you're just pushing them through this channel. If you look at the force that they apply on the terminus, it agrees pretty well with kind of a simple kind of continuum theory, but the fluctuations are huge. You can't escape stochasticity in these problems. You can go from something that's twice what you would expect kind of from a continuum model, or it can get extremely low. So you might imagine that sometimes you can be in a highly jammed state with a really large force, but then suddenly unjam And this could lead to this decoherence, and then the release of stress allows these big calving events to happen. And so it's this huge variability in the flow of granular materials that we can't ignore these fluctuations, which we think are really controlling the calving events here. But this is kind of ongoing work in the lab, ongoing experiments, and hopefully we'll have a little bit more to say soon. You know, it's funny, I had prepared like a whole another part of the talk telling you about what we're doing with atmospheric physics, but clearly I won't have time to talk about that. So I'll just end with my acknowledgements, which is maybe kind of the most important part of the talk, you know, kind of recognizing all the people that's worked on this. We've had a number of Emory grad students, but a lot of Emory undergraduate students work on this as well. Kavinda is a graduate student. Josh is a postdoc, was a postdoc with me. Now he's about to start a lab at Portland State University. And he made contributions to a number of projects in the lab. And Nandish, Lin, Toyin, Jake, Tianshu, and were all undergraduates that made contributions. And Dana was a graduate student who just recently graduated. I didn't get to talk about his work as much. But so with that, I think you know, I'll kind of wrap up and take questions, and then just emphasize what I wanted at least the audience to take away is that you know, I think a lot of problems in climate physics don't necessarily have to be, you know, just modeling of the way, you know, the atmosphere flows on our planet. That's an extremely important part. But there's all these other really cool problems, from microscale processes to, you know, to basic fluid mechanics and nonlinear dynamics that have direct impact on thinking about Earth's climate and variability. And, you know, hopefully I've convinced some students that, you know, maybe they should read up some more and, you know, get interested in some of these problems. We could always use more great people in the community. So with that, thank you very much.
Thank you, Justin, for the beautiful talk and just highlighting the role of the experiments. And so we have time for questions. So please put your questions in the chat. Let's see, well, Pedron has a question.
Well, actually, I think while people are entering their questions, Justin, maybe you can use 2 minutes and show those the slides about your work on the atmosphere, the second part of your talk, if you want. Because this is recorded, even if you spend 10 seconds, people can go back and look at it.
Oh, that's a good point. Yeah, you know, I mean, I wanted to kind of highlight a range of things that are going on, you know, and if even one part of a student or, you know, somebody sees one part and is really excited about it and goes off and learns more about it, I think that then I think that it's been a success. But yeah, I'm happy to. Sorry, I'm going to fly through some flies and get all the way to the end. I apologize. I had stopped sharing my screen, and so now I have to go back through. Okay, yeah. So we've been thinking about dust in the atmosphere lately, and particularly one problem that, you know, we got interested in is that they find huge particles of dust that are blown many thousand, or, you know, thousands of kilometers further than they should, right? So like 100 micron size piece of dust, you know, if you do a basic fluid mechanics problem, you'd think it should fall out of the atmosphere right away, but it doesn't. And so the question is why? One theory is that people have you know, thought that this dust could be affected by electrostatic forces, right? And, you know, there's like 20 teragrams of dust in the atmosphere, and it's actually really important for interacting with radiation, but also in transporting nutrients. I think well, I think more than 50% of the nutrients apparently that you know, feed the Amazon rainforest are blown from Africa, is one of the statistics. And so what do we do in the laboratory? Well, we levitate dust. You know, we take these acoustic levitators and we levitate individual particles. And in this particular experiment, we just wanted to know a very simple question: how long can an isolated particle stay charged? You know, It's similar to the question of, I rub a balloon on my head, how long does the balloon stay charged? But, this is a tiny particle. And if you charge up a single particle and just let it sit there, how long can it stay charged? And the way we measured it is by dropping it into this Faraday cup using the acoustic field, changing the phase of the acoustic field and moving it around. And we did that for weeks. We used all different kinds of particles, plastics, organics, puffed amaranth, pumice, things that could be easily levitated. And what we found is that, at low humidities, these dust particles, or analog dust particles, could stay charged for weeks, or at least a week or more. And it kind of wasn't dependent on particle size either. And as you increase the humidity, this time scale decreases. I could tell you all about our model for why this is, but what we basically found is that this could be really important for kind of 20 micron size dust, using electric fields that are typically found in the atmosphere. It doesn't have to be just thunderstorms and stuff like that. Even fair weather electric fields can play a role. So, particle charging and electrostatic forces can be important for dust in the atmosphere, is kind of the one conclusion from this. But nowadays we're thinking about how microbes might live on these particles, and people know that if you go just suck up dust from the atmosphere, you can find tons and tons of microbes, even bacteria, things that don't form spores, are culturable on this dust. So is this its own biome? We know the ocean and soil have very sophisticated biomes. Is the atmosphere just a transport system, or does it have its own biome as well? That's one question we've been thinking about. So we're starting to look at problems where I'll just where we are levitating particles and thinking about how bacteria might grow on these particles, and how that they might be affected by temperature and precipitation and radiation and things like that. So there's a biological component to it as well, which can be addressed in the lab. But messing with these acoustic levitators is a really fun project.
Can you put many particles there?
Sorry, that might sound kind of wild
so cool.
compared to other atmosphere stuff.
Can you put many particles there, or is currently only one can float?
No, we can do many particles. They tend to get very dynamic. If you put lots of particles in there, they dance around and they do all kinds of things. Right now we're kind of sticking with one, but are interested in putting more in there. I did see there was a question. What do you think is the most important remaining unknown problem associated with predicting glacial motion? Is it the rheology within ice, sliding at the base, ice melange, or melt channels? Oh, that's a great question, Doug. Put me on the spot. Look, so I would say, okay, so when you say predicting glacier motion, I'm going to assume that kind of means really thinking about evolution in terms of sea level rise. What do we expect to happen in the next 10 years, 50 years, 200 years? And I would say the way the glaciers interact with the ocean is kind of the most important part, not just because that's what I've worked on. I mean, the sliding laws and the rheology are part of that, because, how the ice is moving on the land will determine how fast it gets to the ocean in some regards. But one thing that we found in the last 10 or 15 years is that melting from underneath, the ability of warm waters to come underneath and undercut this ice that overhangs into the ocean, and how much faster it's melting because of that's been a huge story. So I think, there's a lot of questions at the intersection of oceanography and glaciers that are really kind of been surprising in the last 10 years. So I would say it's that boundary condition. What is happening at the boundary of the ice in the ocean? Abby Plummer asks, so for both the ice melange work and the levitation work, how strongly do your results depend on particle shape? Very, very much so. So I can give you an example. I don't think I have the. Let me go back to one of my videos here. Okay, so Okay, so here you see these kind of Lego looking particles that are being pushed through the channel. And there's a reason we wanted to use particles that look like this. If you use spheres, you can't even get them to form a wedge, really. They just kind of spread out and form a monolayer. They have friction, but it's not enough to really make them, you know, kind of jam up. So in this case, for these floating granular materials, it makes a huge difference. Spheres are very different than other shaped particles. Part of that reason is, you know, you have to remember you have a floating, the water surface here is essentially zero friction. So if I have like an inverted underwater sand pile, that will spread out into a monolayer unless I provide some sort of confinement or or ways for the particles to experience more friction than just contact between spheres. So we quickly did away with spheres, and they're not useful at all, actually, for these experiments, except for understanding maybe what controls the expansion of floating granular materials, but with the relation to real ice melange in the experiments. Yeah, it's very important. Particle shape is important.
Can I also ask a follow-up question? Because I didn't see
Okay.
other questions. Yeah, so it was interesting to hear the effect of particle shape, and when you talk about the coherence the coherence of melange before and after the cupping event, that was based on the model is based on spherical particles, right? So can you use these experiments to study the coherence,
Well,
right?
Yeah, we did something. Okay, so what did we do here? So we fixed this granular material of spheres. Let's say it's 8 kilometers long. It's a computer, so it can be as long as it wants to be, right? So it's 8 kilometers long, and then we let it expand by 0.1%. And then we fix it. We just, you know, there's a wall on the other end. It's not really open. We're holding it, and then we let it expand by 0.1%. And we look at how the particles moved around in order to accommodate that expansion. That's a process that's really controlled by just steric interactions between particles. You know, they're grains. You know, it's not the rheology, it's just geometry at that point. It's just what is the motion of small particles compared to the overall motion. And in that case, it's okay to just use spheres. But if I was actively pushing this and there was friction involved and there was an open channel on one end and all these other things, then the particle shape is really important. We kind of just tried to use the simplest model here to get across that this, you know, decoherence is really just a fundamentally geometrical effect of what happens in a granular material. How is the local tiny strain of particles related to the overall strain in granular materials?
Got it. So it should be robust for different types of shapes.
Okay, so we have another talk. Is there a way?
Oh, there's actually another question.
Another question in the chat. So I'll read it. It's is there a way the elastic modulus of natural ice scale with the model ice materials used in the experiments? My question is geared towards understanding what type of materials are good candidates of model ice in the lab. Well, there's no better model for ice than ice. You know, I would totally be doing experiments with ice, except, you know, ice has this kind of tricky little problem that it melts. And then it makes your experiment go away after a day, right? So unless you have a cold room, but a cold room is expensive. So we don't have, we use plastic, which has the same density of ice, but the main difference is that we're not modeling like fracture or other important processes that happen in real ice in real time. If you're just using plastic blocks that have the same density of ice, you can laser cut them, you can cut them with a bandsaw, you can, you know, form them and shape them in other ways, but you're not going to be able to look at those granular processes like that involve, you know, active breaking of ice or fracture or elastic fracture. You can use hydrogels and other things. So I didn't mention this, but Lori Sayag is a kind of applied mathematician and physicist who's used xanthan gum and other kind of hydrogel-like materials that flow with a non-Newtonian rheology, but if you push them hard enough, they'll actually fracture. And so you can use kind of hydrogel-like materials to think about kind of active fracturing processes and even long-scale flow of ice. So people have used things like that to model ice as well.
Great. Okay. Okay, there are no more questions. Let's thank Justin again for a really inspiring talk and overview of all the recent the interesting questions we can answer with experiments.
We
And the
have
next
one more
talk.
question, if that's okay.
Oh, yeah, sure.
What do you expect to change if the floating granular ice is melting at the same time? Yeah, that's a great question. And so that's something that we're trying to work with some oceanographers, Rebecca Jackson at Rutgers, to model some of these things. I mean, clearly that would make the, first of all, that injects a lot of cold water into the fjord, which it kind of affects circulation. And so there's a bunch of oceanographic consequences of the melting ice, but it also changes the distribution of sizes of icebergs. They're going to be smaller as you get out further in the fjord and bigger as you get closer to the terminus. I wouldn't expect it to change our 0th order qualitative or even quantitative conclusions from what we did, but certainly maybe in the way the ice jams and how maybe it even gets more round as it melts and things like that. So I think it's a 2nd order effect, but I think its primary thing would be injecting cold fresh water into the fjord. That would be a big issue.
All right. And I guess before we leave, I want to mention the next GPC talk will be May 17th by Andrew Thompson from Caltech. So stay tuned. Are there more questions for Justin?
Thanks, everybody. I really appreciate you inviting me to give this talk.
Thanks, Justin. That was great.
This is great. Yeah. Okay. All right. Then, yeah, let's wrap up.
Yeah.
Thank you.
Okay.
See you all in a month.
Bye, everyone.
Cheers.
Bye.
Yeah. Bye.